All right, so this is lesson 1 of trigonometry. I'm going to go through the trigonometric identities part, and this is the proofs and stuff. I will have gone through all this stuff in class, so we won't worry about that so much. We're just going to skip right on to lesson 1. So lesson 1, reciprocal, quotient, and Pythagorean identities. So remember from our unit circle that we basically set this up. That we had, if we have our little angle over here, our r, our y, and our x, and then we saw that by basic SOHCAHTOA, we know that sine is y over r, cos is x over r, and tan is y over x. Again, that's our sine, cosec, tan. And so that ends up being something that's true. Now, this creates some things that are a little bit different that we haven't been exposed to yet in the course. And these are called identities. And what an identity is something which is always true. Now, this is comparable to an equation. An equation is something that is sometimes true. So, for example, if we have an equation like 2x plus 3 equals 11. I could solve this equation by subtracting 3 from both sides and arriving at the fact that x equals 4. Now, because x is a variable, x could literally be anything we want it to be. What we typically talk about is what value of the variable solves the equation and things like that, but x could be 2. If x would be 2, this is just a false statement. So equations are true under certain circumstances versus an identity which is true always, under all circumstances. So let me give you an example of an identity here. A fairly classic identity is the difference of squares identity. A squared minus b squared equals a minus b multiplied by a plus b. Now this is true no matter what values I choose for a and b. No matter what. I could choose 7 and 4. 7 squared minus 4 squared. 7 squared is 49. 4 squared is 16. So this ends up having a value of 33. And if we do this over here, this becomes 7 minus 4. And this becomes 7 plus 4. This is 3 times 11. So again, in an identity, the identity is always true. Always true, no matter what. Equations are only sometimes true. And then when we solve the equation, we're literally finding the single or few value or values that solve the equation. So, here we are dealing with, let me just delete that page now so it doesn't get back in the way. Identities and trig identities. One of the things that we will spend a lot of time with is proving that an identity is true. To prove that an identity is true, you need to show that the left side and right side of the thing are equivalent to each other under all or most circumstances. Now, your formula sheet is covered in identities. That whole right side of your formula sheet, basically all of trig, is really just identities practice. So let's start rocking through this and getting to see how these things come together. So these are all from your formula sheet, and our basic identities we know to be true. Now, I'm going to show you guys why the Pythagorean identity is true. I'm going to try and demonstrate that sine squared of x plus cosine squared of x equals 1. Well, again, going back to our basic definitions of these things, we know that sine is y over x. Or sorry, y over r. Sine here. Cos is x over r. And that equals 1. So we're going to try and show that this is true. Now, we can't assume that it's true. So I'm going to, instead of using an equal sign, put a line down the side. And my goal is to prove that it is always true for all values of x. And again, what that looks like is just algebraically rearranging these things so that it works. So, let's start off. This just becomes y squared over r squared plus x squared over r squared. And then I can go, wait a sec, I've already got a common denominator here. So y squared plus x squared over r squared equals 1. Now that doesn't look like 1 necessarily yet. However, if I look at it a little more closely, I can think back to the old unit circle, and the equation that defines our unit circle is x, y, and r, and by Pythagoras' theorem, x squared plus y squared equals r squared. Now, to be honest, this works for all circles, not just the unit circle. But what I can see is that this thing is the same as this thing. So over here, instead of y squared plus x squared, I could write r squared. And then I have r squared over r squared. Hey, look, that's equal to 1. Now, I've made my left side of my equation equal my right side, and that's been proved to be true under all values. Not just some values, not just sometimes true. I've shown this now to be true no matter what values I choose for x, y, and r. And I've now proved this thing. I've proved that sine squared plus cos squared equals 1. So, that's what we're demonstrating here. Now these ones we've already been using. We've defined all of our reciprocal identities in terms of their reciprocals. And again, you could rearrange it, either one. The quotient identities, again, those are on your formula sheet. Once these things have been proven and are on your formula sheet, you can kind of use them as tools to now not have to reprove them. You can just go, all right, everybody knows this to be true. And from this next step, I can go to here, and that's how you can sort of not have to rebuild all these things from the start. You can use some of these relationships. The cotan, cosecant, and tan secant squared, I'll demonstrate later on in future lessons. We won't worry about that yet. But hopefully, you feel comfortable that I've now proved this thing to be true under all values. Or I should say most values, because it turns out that this is only valid. Did I delete that? I did not. This is only valid when r isn't 0, right? The radius can't equal 0 because if the radius were 0, it doesn't make sense any longer. Okay. Back to here. We're almost getting started here. And these identities are basically the tools that you will use down the road to prove other identities, more complicated things that we haven't seen yet. All right, off to the races. So basic tools that we can use, algebraic strategies, fall into basically 3 groups. Factor expand, common denominator, which is the same as combining fractions. I know that common denominator is not a verb, but I think it ought to be. I would put it forward as a verb. And then the last is multiply by the conjugate. If you've forgotten what the conjugate is, it's the equivalent term. So a minus b and a plus b are conjugates of each other. So this is a bunch of different strategies. If I was getting a common denominator here, I would multiply top and bottom by c. So now CA plus B all over C. If I was doing that with trig, again, I'm going to have to multiply top and bottom by cos theta. So now I get sine theta cos theta plus sine theta all divided by cosine theta. So that would be a step in the process. We can also do some factoring. This is a difference of squares, a minus a, or 1 minus a squared. We typically don't have to do a lot of other kinds of factoring, more than difference of squares. We'll use difference of squares an awful lot through this unit. So make sure that you're feeling comfortable with that. If you're not, that you get comfortable with it. But this would be 1 minus a times 1 plus a. If I was doing this with sine theta, it's going to be 1 minus sine theta and 1 plus sine theta. A squared minus b squared is going to be a minus b times a plus b. Secant squared theta minus tan squared theta is going to be secant theta minus tan theta, and secant theta plus tan theta. Now, multiplying by the conjugate, which we've used already as a tool in rationalizing our denominator. So when we've done things where we're saying, hey, rationalize the denominator of this thing, we've already used this strategy or this tool to accomplish that task. In this particular case, what we're now going to be doing is multiplying or rationalizing things that really are rational all the way along, so they don't have that same problem of rationalizing, but we're still going to use the same tool, multiplying by the conjugate. So here the conjugate of this is root 5 minus root 2. Again, we're dealing with fractions. I have to do the same thing, top and bottom. Now, the root 2 is going to multiply to those two things. It's going to be root 10 minus, now root 2 times root 2 is root 4, or just 2. This is going to end up being 5 minus 2. If we're foiling it all out, we'd have root 5 times root 5, that's 5. Root 2 times root 2, that's 2. And we would end up with a positive root 10 and a negative root 10, which would end up canceling each other out. So this final answer is going to end up being root 10 minus 2 all over 3. If we're doing the same thing in trig world, the conjugate of 1 minus cos is going to be 1 plus cos of theta. Again, top and bottom. Now this becomes 1 plus cos theta, all divided by, remember if I multiply this out, this is my difference of squares, except taking it forwards, multiplying by the conjugate. So this is going to give me exactly 1, which is 1 squared, minus cosine squared of theta. And so that's how that one has sort of come together. Whew! Hopefully you guys are keeping up. Or, again, pause the video. If you're like, what the heck is McManus talking about? Pause and rewatch these things. It makes more and more and more sense as we go through this unit. Trust me. This is a hear me now and believe me later sort of moment. All right. So, next up here is when we're going to be trying to turn all of these big messes of stuff into a single trig ratio. So, first off, part A, tan x cotan x. Well, I could write tan as sine x over cos x. I can write cotan as the reciprocal of that. Now, if I'm not sure of that, again, I can go back to my formula sheet. We've got them on here. Do we agree that cotan is just cos divided by sine? And there's no single way of doing this, which is one of the things that makes it hard, is that you could solve the same thing like 4 different ways, and they would all be right. So that's something to get used to. Cotan is then cosine of x over sine of x plus, now this is sine of x, and then cosecant of x is 1 over sine of x. So now I can just do a bunch of canceling. Boop, 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 boop. The sound effects are super key. But anyway, this whole thing canceled off, so it just became 1. And over here, this became 1. So this whole thing, this big mess, is just a really weird way of writing 2. That is equivalent to the value of 2. We've just written it in a different form. All right, this guy here. Hopefully you can see that I'm going to do some common denominatoring, but the things that I'm working with in my common denominator are in fact conjugates of each other. So my common denominator is going to become 1 plus cosine of theta, and 1 minus cosine of theta. And then if I multiply, this is going to become a 1 minus cos in my numerator over here. And this is going to become 1 plus cosine theta up here. So now what I've got is 1 minus cos theta plus 1 plus cos theta. And now with any luck, you can see that this negative cos theta and this positive cos theta cancel each other off. And my denominator, I'm going to multiply that back together. I'm going to expand these two things just because I see that it simplifies. So my numerator is 1 plus 1. So there's 2 in my numerator. My denominator is going to be 1 minus cosine squared of theta. Now again, we really should be writing this as cosine of theta all squared. But when we're writing this 4,000 times in the course of one proof or one verification or one identity, we get really tired of drawing those brackets. So this is a fantastic shortcut. At first, this shortcut seems awkward. By the time you're done this unit, you will be thanking the math gods that somebody was like, no, wait, way too much writing to do here. Okay. So now 1 minus cos squared. Whenever we see that, that should excite you. You should be like, oh, thank the Lord, hallelujah, I'm at a place that I know where to get to. I've been here before. I understand the 1 minus cos squared theta. So coming back to here, 1 minus cos squared theta is one of our different ways of writing this. If we just subtract cos squared from both sides, that gives me this form. So sine squared equals 1 minus cos squared. Now, these three forms are on your formula sheet. The rest of these are not on your formula sheet. Now, they're easy to spot, and I get by the time they will seem strange now, but by the time we get done with this unit, you'll be able to do all of that no problem at all. Okay, next page. I'm almost there. This whole going back and forth thing is kind of a nuisance. Alright, so you guys won't recognize anything, time has passed, but I just downloaded the formula sheet so I don't have to keep scrambling back and forth through the document here to get there. Anyway, so back to here. We'd now arrived at 2 over 1 minus cos squared. But remember, we just saw that 1 minus cos squared is just a fancy way of writing sine squared. So this becomes 2 over sine squared of theta, which is the same as 2 cosecant squared of theta. Again, just because 1 over sine is the same as cosecant. Okay. Onwards. Cosine cubed plus sine squared cos x. Now this is easier to see if I put some costumes on this. Instead of cos, I'm just going to write c. And instead of sine, I'm just going to write s. Hopefully you can now see I can take out a common factor here of cosine. So I'm going to take out cosine of x. What I'm going to have left is cosine squared of x plus sine squared of x. That looks familiar. Hopefully in your head you're screaming, wait a sec, I know that thing, I know that thing. Cos squared plus sine squared is our happy place. Cos squared plus sine squared is exactly 1. So this whole big mess is just the same as just cos x. Right? Because cos x times 1 is just cos x. Whew! All right. Off to the races. Are you feeling it? You loving this? Probably not yet. That's okay. You will. Now, secant squared minus tan squared. Whenever you see something squared, it should hopefully stir in you this emotion of like, I feel like I kind of know what to do with it. And what I'm going to do with it is look at my formula sheet. So we're going to play out our formula sheet and see what we can find here. So secant squared minus tan squared. Is that what that one was? Let me go back to this really quick. Yeah, so see how I've got this secant squared minus tan squared thing? Secant and tan kind of go together in important ways, and we'll see that multiple times over this unit. Again, you'll have a visceral feel for these. Right now, we don't, and that's okay. But I can see that this is kind of like this thing. All I'd have to do is rearrange it a little bit. So if I took this and subtracted tan squared from both sides, then I will see that secant squared minus tan squared equals 1. I wish I could write on this thing. You know what? I can. I should really pause this instead of just you having to watch me do this, but that's okay. Almost there. Show all, smart notebook writer, print. Okay, now I'm going to go back to here. But so anyway, secant squared minus tan squared, this thing is 1. So I end up with 1 minus cosecant squared of A, all divided by cos squared of A. Now, yeah, go away. So 1 minus cosecant squared, hey, that's a thing too. So now if we go back to our formula sheet, yes, open. Come on, move. Cosecant is cotan squared plus 1. So, if we went back to here, again, I apologize, I'm skipping all over the place. But since cosecant squared was 1 minus, cosecant squared was 1 plus cotan squared. And now again, with any luck, we can see that over here. And I can write on this copy, which is kind of nice. So again, I took this cosecant squared and I turned it into 1 plus cotan squared. Okay? Back to here. Whew. Now this one and this one cancel each other out. This negative is going to distribute in here. So I get negative cotan squared of A, all divided by cos squared of A. Now cotan is cos squared over sine squared. So now I could write this, and my apologies, I'm going all over the place here. This is going to be negative cosine squared of A divided by sine squared of A divided by cos squared of A. And I'm going to put that over 1 so we can see this. This is going to flip to negative cosine squared of A over sine squared of A times 1 divided by cosine squared of A. And now this and this cancel each other out. So this becomes negative 1 over sine squared. And whenever our sine squared is in the denominator, what we want to think in our own head is, hey, wait a sec, that's just cosecant. Huh? So this whole thing, in all of its ugliness, just turns to negative cosecant squared of A. Holy curmudgeon. Anyway, there you go. Hopefully that made some sense in some way, shape, or form. This is the last one here. What do we see when we look at this? Well, hopefully some conjugates. But I'm actually going to do something else instead of conjugates on this one. I could do it with conjugates. I think it's going to make more sense here. And a good strategy is typically to turn them all into sines and cosines. It's not always the most the easiest or fastest strategy, but it's a technique that works an awful lot. So I'm going to turn everything into sines and cosines. It's not always the most elegant strategy. That's what I was looking for. So this is going to become sine theta minus 1 over, let's change that around. It's not sine theta minus 1. The tan turns to sine theta over cos theta. Right, again, because formula sheet. Minus 1. And then cotan is cosine theta divided by sine theta. Okay? So again, hopefully that makes sense. Now what I'm going to do is I'm going to common denominator from here. So this becomes sine theta minus, this is going to be cos theta over cos theta, right? And showing my common denominator in here. Here I'm going to have sine theta over sine theta. So this is going to be sine theta minus cos theta, all divided by cos theta. And this is sine theta minus cos theta, all divided by sine theta. It's coming together, it's coming together. Now, we could take these weird fraction things, and instead of dividing them, I could multiply by the reciprocal. So this is going to be sine theta minus cosine theta, all over cosine theta, times the reciprocal of that. So I'm going to flip it. Sine theta over sine theta minus cos theta. Then that term and this term cancel. Sorry, it's not a term, it's a factor, right? Which is good because you can't cancel terms, but you can cancel factors if everything's factored. So those factors cancel, and then I end up with sine theta divided by cosine theta. And that's my answer, because that, my friends, is tan theta. And I know most of you, if not all of you, are like, how does he just know these things? When you've practiced them enough, you will hardly need to consult your formula sheet, because all of these things will just be in your brain. You will be able to just be like, oh, hey, look, there's sine theta over cos theta. Wait a sec, I recognize that. That's just tan theta. Anyway, we'll get there. We'll get there. Hear me now and believe me later. Whew. All right, so here's example 1. Done. Love it. Onwards. We can also verify a trig equation. So basically, or an identity. There's basically two things we can do. We can say verify or prove. Verify just shows that it works with numbers. Now, if we're showing this that it works with like 1 or 2 or 3, we've demonstrated it over some limited recognition. But if we show that it works for all, then that means it proves. So it's not a proof, it's just a step that allows us to do a faster than proof. We can see if something seems to make sense. Okay, so here we go. Here we get cosine squared equals sine squared plus 2 cos squareds minus 1. All right, so we're going to show that this is true using a value of theta equals 300. So we're going to use our unit circle heavily with all these verification things. So 300 is right there on my unit circle. My coordinates there are positive 1/2, comma, negative root 3 over 2. Right? So we're going to use those coordinates to know these values. So cosine squared of 300. Well, cosine of 300 is just 1/2. And then the whole thing is squared, becomes 1/4. Again, hopefully people are comfortable with that. and cosine is 1/2 because sine e cosec tannum. The sine is the y, the cos is the x, the tan is the slope. All right, so I got a quarter. Now what I'm going to do is I'm going to do the right side of the equation. Now, first off, my sine squared. Well, sine is my y, so it's going to be negative root 3 over 2, all squared, plus 2 times cosine squared. Cosine squared of 300 is going to be that 1/2. And then minus 1. Okay, so hopefully we can now manipulate this. Negative root 3 squared is positive 3, so this is just 3/4. This one up here is going to be 2 times 1/4. And then this is going to be minus 1. Now, we could reduce that, but we don't want to because we want to really get everything to the same denominator. So this is going to be 3 plus 2/4 minus 4/4, right? 1 is just 4 over 4. So this becomes 5/4 minus 1 is, or minus 4 is now 1/4. And hey, look, the left side and the right side are the same. Did we prove this? No. We just showed that it happened to work for 300 degrees. We don't know that it works for all angles until we can prove it with only variables. We could also just plot these graphically. So if I was going to plot these graphically, I can just go by the way, this whole proving thing is a very math thing to do. In science, we can't prove that things are true. We can show that they've been true forever, and we can assume that they will stay being true, but we can never prove that these things are always true. In a logical perspective, we call this proving by induction or demonstrating by induction. We're showing that it's worked for some set of values, could be even a lot of values, and then we're saying, so it should hold true for all values, but not proved. Now, what I'm going to do is I'm going to go up to here. Sorry, I'm having a metaphysical discussion while I'm doing this. But I'm going to put this as the thicker line. So what I'm going to do now is I'm going to graph both things. And I'm going to put it from window negative 360 to positive 360. I'm going to change my mode to degrees. And now I'm actually going to change my y values here as well. Probably don't need to see all that high. Let's go 3, negative 3 to positive 3. And then let's graph this sucker. So there's my first graph. This is that sine squared. No, cosine squared? Well, I don't know, whatever the hell it was. Now look, there's the other one. Hey, see how it's just duplicating what was already done? If you want to be extra sure, I could go to the table of values and just see that the table of values seem to be always the same. Does that mean that they will be always the same? No. It just says that they've been always the same so far. It's not a formal proof until we can algebraically demonstrate it. But again, this is going to look something like this. And then the other curve did the same thing. And that's a pretty strong indication that something is an identity, even if we haven't yet proved it. Okay, now, oh man, we're throwing lots at you. My apologies. That's why I wanted to video this so that you could watch it and rewind it and delete it and get angry and whatever you need to do, but we're going to go through these pieces. So, non-permissible values in an identity are determined by finding the restrictions. Now, there are two kinds of restrictions, okay? Two kinds of restrictions. The first is that there are built-in, or what I like to call precursor limitations. So, tan, secant, cotan, and cosecant all have built-in limitations. Not cos. CSC is what I meant to write there. Let's fix that up. So cosecant, secant, cotangent, and tangent all have built-in limitations. The reason they have built-in limitations is even if I don't see it, they all have sine in the denominator, right? Tan is cos over sine, secant is 1 over sine, cotan is sine over... Oh, what the hell did I do here? No, back that up. Whoop, whoop, whoop. Pretend that none of that happened just now, okay? Tan is sine over cos. Secant is 1 over cos. Right? There's like cos in every pair. Cotan is cos over sine, and then cosecant is 1 over sine. So here these have sine in the denominator. Sine can't equal 0. And for these two, right, remember sine is 0 on the horizontals. Right? Sine is 0 there and there. So cotan and cosecant are 0 plus pi n. That's the limitations for cotan and cosecant. It can't be any multiples of pi. It can't be 0 pi, it can't be 1 pi, 2 pi, 3 pi, 4 pi. You get the picture. Tan and secant, on the other hand, tan and secant are undefined when cos is 0. And that's my vertical lines. Right? So that's my pi halves, 3 pi halves. So my limitation here is pi halves plus pi n. So built-in limitations. Anytime you see one of these cosecant, secant, tangent, or cotangent, you always know that there's a non-permissible, and you can just write that right out. So those are the built-in restrictions. Also, anytime there's a denominator, at any point in the proof, then any zeros in the denominator are also non-permissible. So again, there's two kinds of non-permissibles. There's the precursor or the pre-existing non-permissibles that you get with tan, secant, cotan, and cosecant. And then there are situational non-permissibles. A situational non-permissible has something in the denominator, so you go, it can't be 0 because of this. And you solve it out sort of like a little mini equation. Okay, state the non-permissibles in degrees and radians of the variable for each trig ratio. No, we just kind of did that. Anyway, tan x. Tan is undefined at my vertical lines, again, just because it's the slope, or we can think because it has cosine in the denominator, and cosine is 0. So this is going to be pi halves plus pi n, or 90 plus 180n. And again, as a blanket statement for all of these, I'm just going to write n is an element of the integers. N-E-Z. N is an element of the integers. Okay, cotan. Well, cotan, again, we know has sine in the denominator. So cotan has sine in the denominator. Sine is 0 here and here. So, well, and it's technically x cannot equal the limitations. X cannot equal here just pi n. You could write it as 0 plus pi n, but that's just the same as pi n. Again, secant is 1 divided by cosine. And again, cosine is 0 on my verticals. So here and here. Right? So same limitations as this. Oh, I keep forgetting to write them in degrees as well. Oh. You'll excuse my lack of really clear thinking if you check the time. Anyway, down here, this is just going to be 180 times n. So 180, 360, 540, etc., etc. And then cosecant is the same. Cosecant is 1 over sine. Right? From your formula sheet, or just because you know each one has a co. And sine is 0 here, so it's going to be x cannot equal pi n or 180 n. And again, on all of these, n ez, right? That's just, instead of writing that every time, we've made a blanket statement. Okay, so determine the non-permissible values of this thing. So right off the bat, I see that a tan, secant, and cotan all exist in the question. Because I see that, I know there's a bunch of built-in non-permissibles that I'm going to just deal with straight off. So tan is pi halves, 3 pi halves, etc., or pi halves plus pi n. Secant is the same, and then cotan is pi n, or 0 plus pi n. And so I've already identified on my unit circle all of these points. So that's just my starting point. Now I have to look at my situational. My situational ones are that because there's a denominator, secant x cannot equal 0, and cotan x cannot equal 0. Okay? Now, secant x is never 0. This does not happen. Okay? That's not a thing, so you don't need to worry about it. Cotan of x would be 0 when, remember that cotan is cos over sine. So cotan will be 0 when cosine is 0. When the numerator is 0, that means that the whole thing is 0, assuming that the denominator is also not 0. But so my 0 is my numerator when cosine, so that's going to be my situational, which we've already included, but now we've thought through all of the possible things. So the non-permissible values are x cannot equal pi halves plus pi n and just pi n, or we could rewrite this instead of one statement or two different statements. I could go, wait a sec, all of my solutions are exactly pi halves or 90 degrees apart. So I can just go x cannot equal pi halves n. And that one statement does incorporate. Now, that's not technically better or more correct than this. On the diploma and on any test that I'm giving you, I would give full marks for both of those. You don't have to see the summarization piece. You don't have to see how they can combine. All right, that's that. I'm going to leave this here. Hopefully this makes sense. Please watch it again and again and again. Come in and get extra help. I will make more of these videos to help so we can get through this as painlessly as possible. All right, thank you all.